You are standing in the middle of an invisible desert, a bubble of emptiness so vast that light takes 1 billion years to cross it. Every galaxy you see, every cluster of stars, even the supercluster containing your home galaxy, floats inside this void. Scientists call it the Keenan-Barger-Cowie void, the largest hollow ever discovered in space. Recent measurements show we are 100 million times more likely to be trapped inside this emptiness than living in normal space. This void changes how the universe expands around you. It warps time itself. If you enjoy discovering how isolated and strange our cosmic address really is, consider subscribing to the channel. The evidence keeps mounting. Prepare yourselves. We begin. Something is fundamentally wrong with where we are in space. For over a decade, astronomers avoided discussing it. They rechecked their measurements. They questioned their instruments. In 2013, 3 researchers named Ryan Keenan, Amy Barger, and Lennox Cowie published findings that should have shaken cosmology to its core. Our galaxy sits inside a region that contains far fewer galaxies than it should. This region measures roughly 1 billion light-years across. Think of it like finding yourself in an enormous bubble inside the ocean, except this bubble spans distances that light takes eons to traverse. The void surrounds our Milky Way completely. Everything you observe in the night sky exists within its boundaries. The Andromeda Galaxy, 2.5 million light-years away, floats in the same emptiness. The Virgo cluster, containing over 1,000 galaxies, occupies the same hollow. Even the Laniakea supercluster, which holds 100,000 galaxies, including our own, resides entirely within this cosmic desert. Scientists measured the density of matter in our region compared to the rest of the universe. The result was startling. Our neighborhood contains roughly 20% less matter than average space. What makes this discovery particularly unsettling is how long it took to confirm. Astronomers had suspicions for years. Galaxy surveys showed peculiar gaps in distribution. Distance measurements revealed unexpected patterns. Yet accepting the truth meant acknowledging that our position in the universe violates basic assumptions. The cosmological principle states that on large scales, the universe should look the same everywhere. No location should be special. No region should be dramatically emptier than another. This void challenges that principle directly. The Keenan-Barger-Cowie void, named after its discoverers, qualifies as the largest known void in existence. Average voids span roughly 140 million light-years. This one measures 7 times larger. To put that in perspective, imagine standing in a football stadium. Now imagine that stadium sitting inside a city. The city sits inside a state. The state occupies part of a continent. This void, compared to normal voids, is larger than that entire progression. The scale defies easy comprehension, but here is where it gets stranger. In 2017, another research team verified the findings using completely different methods. They analyzed the kinematic effect on light passing through galaxy clusters. The movement patterns matched predictions for a massive underdense region. Then, in July 2025, researchers presented evidence at the National Astronomy Meeting. They examined baryon acoustic oscillations, which are pressure waves frozen in space from the early universe. These waves act like cosmic rulers, measuring distances and densities. The conclusion was definitive. We are 100 million times more likely to inhabit a void than normal space based on current observations. Something placed us here. Something created this emptiness. The implications are only beginning to emerge. Ryan Keenan was a doctoral student when he noticed the pattern. Working at the University of Hawaii, he spent months analyzing galaxy catalogs, counting how many galaxies appeared in different regions of space. Standard cosmological models predict that matter distributes fairly evenly across large distances. Small variations exist, certainly. Dense clusters form in some areas. Sparse regions develop in others. But extreme differences should be rare. Keenan kept finding the same troubling result. The local universe around our galaxy showed significantly fewer galaxies than models predicted. His advisor, Amy Barger, encouraged him to dig deeper. They expanded their survey. They cross-referenced multiple data sources. They checked for measurement errors and observational bias. Every test confirmed the original finding. Our cosmic neighborhood sits in a profound underdensity. The void extends roughly 1 billion light-years from its center, and our galaxy resides only a few 100 million light-years from that center. This positioning matters because it means we experience the void's full effects. The research team published their results in 2013. The paper included detailed density profiles showing how matter increases with distance from our location. Near the void center, density drops to roughly 54% of the cosmic average. Moving outward, density gradually increases. At the void's edge, matter concentrates into a thick shell of galaxy clusters and superclusters. Beyond that shell, normal cosmic density resumes. The void has clear boundaries and a definable structure. Other astronomers responded with skepticism. Large voids were known to exist, but one this massive seemed implausible. The standard model of cosmology, called lambda cold dark matter, struggles to explain such extreme underdensities. Computer simulations of cosmic evolution rarely produce voids this large and deep. The probability of such a structure forming randomly is extraordinarily low, yet the evidence kept accumulating. In 2017, Benjamin Hoshit, an undergraduate student working with Barger, approached the problem differently. Instead of counting galaxies, he examined the cosmic microwave background radiation. This radiation, leftover light from the Big Bang, passes through all structures in the universe. As it travels through galaxy clusters, the light shifts in energy. This shift reveals how fast those clusters move through space. Galaxy clusters inside voids should move differently than clusters in normal regions. They should be pulled outward by the stronger gravity of denser surroundings. Hoshit measured these movements. They matched exactly what the void model predicted. The scientific community could no longer dismiss the findings as measurement errors. Multiple independent methods confirmed the same conclusion. Then came the most recent evidence. Researchers analyzed 2 decades of baryon acoustic oscillation data. These oscillations show how matter clumped together in the early universe and how those patterns evolved over time. The analysis revealed that a void model fits observations 100 million times better than models assuming uniform density. We are living inside something that should not exist according to our best theories. Empty space is never truly empty. This fact confuses many people when they first learn about cosmic voids. These regions still contain galaxies, though far fewer than normal areas. They still contain dark matter, the invisible substance that makes up most of the universe's mass. They still contain the dark energy that drives cosmic expansion. What makes them voids is relative absence, not absolute emptiness. Think of population density on Earth. Manhattan contains roughly 70,000 people per square mile. Montana contains about 7 people per square mile. Montana is not empty, but compared to Manhattan, it qualifies as a vast open space. Cosmic voids work similarly. Normal regions of the universe might contain 10 galaxy clusters within a given volume. A void might contain only 2 or 3 clusters in the same volume. The difference is dramatic but not total. Our void demonstrates this principle clearly. The Milky Way exists inside it. So does Andromeda. The local group, containing over 50 galaxies, sits entirely within void boundaries. The Virgo cluster, one of the largest nearby galaxy collections, occupies void space. These structures prove the void is not completely empty. What makes it remarkable is the absence of the massive galaxy superclusters that dominate other regions. If you could see the universe from outside, normal regions would appear as bright, dense webs of light. our void would appear as a darker bubble with scattered islands of illumination. The density contrast measures precisely at 20% below average. This figure comes from careful surveys and calculations. Astronomers count galaxies in shells, expanding outward from our location. Close to us, they count fewer galaxies than expected. Farther out, the count increases. At roughly 1 billion light-years distance, galaxy counts reach normal levels. Beyond that distance, the universe looks typical. The underdensity is localized, but this underdensity has profound effects. Gravity depends on mass. Less mass means weaker gravity. In voids, the gravitational pull from the sparse interior matter is much weaker than the gravitational pull from the dense matter surrounding the void. Imagine a ball at the bottom of a shallow bowl. The bowl's walls pull the ball upward more strongly than the bowl's bottom pulls it down. Galaxies in voids experience similar dynamics. They feel stronger attraction toward the void's edges than toward its center. This creates peculiar velocity fields. Galaxies inside voids move outward faster than cosmic expansion alone would drive them. They accelerate toward the denser regions beyond void boundaries. Astronomers can measure these velocities by analyzing light from galaxies. The measurements confirm that galaxies in our region are indeed flowing outward, exactly as void dynamics predict. Understanding what the void means requires accepting uncomfortable truths. Our location in the universe is unusual. The structures around us develop differently than structures elsewhere. The cosmic evolution we observe from our position may not represent typical cosmic evolution. We are measuring the universe from an atypical vantage point. That realization changes everything. Zoom out far enough, and the universe reveals its true architecture. What appears chaotic at small scales becomes organized at large scales. Galaxies cluster together into groups. Groups combine into clusters. Clusters align along filaments that stretch across hundreds of millions of light-years. Between these filaments, vast, empty regions dominate. Astronomers describe this pattern as resembling foam or the structure inside a sponge. The popular comparison, though, is Swiss cheese. The cheese represents the matter. Long strands of galaxies form dense filaments where matter concentrated over billions of years. These filaments intersect at nodes where massive galaxy clusters developed. The holes represent voids. These regions lost their matter as gravity pulled it into the surrounding dense structures. The cosmic web grew through this process of attraction and depletion. Overdense regions attracted more matter and became denser. Underdense regions lost matter and became emptier. The universe amplified its own irregularities. This structure emerged from tiny variations in the early universe. Right after the Big Bang, matter distributed almost uniformly. Almost, but not perfectly. Random quantum fluctuations created regions slightly denser than average and regions slightly less dense. These differences were minute, perhaps 1 part in 100,000. But gravity amplifies differences. The denser regions pulled in surrounding matter. As they gained mass, their gravitational pull increased. They attracted even more matter. The process fed on itself. Meanwhile, the less dense regions lost their matter to nearby dense regions. As matter left, these regions became even less able to hold on to what remained. They emptied out progressively. After billions of years, the small initial variations became the dramatic differences we observe today. Dense filaments contain hundreds of times more matter than voids. The cosmic web is gravity's artwork, carved over cosmic timescales. Scientists map this structure using galaxy surveys. Telescopes observe millions of galaxies and measure their positions in 3 dimensions. From this data, researchers construct maps showing where galaxies cluster and where they are void. The resulting images reveal the foam-like architecture clearly. Filaments appear as bright streaks. Voids appear as dark bubbles. Our own position within a void becomes obvious in these maps. The largest voids span over 1 billion light-years. The The smallest voids that astronomers typically study measure around 100 million light-years. Most voids fall somewhere in the middle, around 2 to 500 million light-years across. These voids make up roughly 80% of the universe's total volume, yet they contain less than 10% of its matter. The universe is mostly emptiness, organized around thin threads of substance. The Keenan-Barger-Cowie void ranks among the absolute largest voids ever detected. Only the Eridanus supervoid, measuring 1.8 billion light-years across, exceeds it in size. Living inside such an enormous void places us in an unusual situation. Most galaxies exist along filaments or in clusters. They have many neighbors. They sit in matter-rich environments. We live in the opposite condition, surrounded by cosmic deserts stretching almost incomprehensibly far in all directions. This structure shapes what we observe when we study the universe. The universe is expanding. This fact, discovered by Edwin Hubble in 1929, revolutionized cosmology. But knowing the universe expands is different from knowing how fast it expands. That expansion rate, called the Hubble constant, has become one of the most controversial numbers in physics. Scientists measure it two different ways. Both methods are rigorous and well tested. The problem is they give different answers. The disagreement has grown so severe that physicists call it the Hubble tension. It threatens to break our understanding of cosmic evolution. The first method looks at the early universe. About 380,000 years after the Big Bang, the cosmos was filled with hot plasma. Light could not travel far through this dense material. Then the universe cooled enough for atoms to form. Suddenly, light could move freely. That light has been traveling through space ever since, growing fainter and more stretched as the universe expands. We see it today as the cosmic microwave background, a faint glow in all directions. This background radiation contains detailed information about the early universe. Tiny temperature variations, measured in millionths of a degree, map out how matter clumped together at that ancient time. By analyzing these patterns using the standard cosmological model, scientists calculate how the universe expanded from then until now. This method predicts the current expansion rate should be roughly 67 kilometers per second per megaparsec. A megaparsec equals 3.26 million light-years. The number means that for every 3.26 million light-years of distance, galaxies move apart 67 kilometers per second faster. The second method examines the local universe directly. Astronomers observe Type 1a supernovae, exploding stars that shine with predictable brightness. By comparing how bright these explosions appear versus how bright they should be, astronomers calculate their distance. They also measure how fast these distant galaxies move away from us by analyzing shifts in the light spectrum. Combining distance and velocity gives the expansion rate. This method consistently yields values around 73 kilometers per second per megaparsec. 6 units of disagreement might seem small, but it represents roughly a 9% difference. In physics, when two independent measurement methods disagree by 9%, something is seriously wrong. Either the measurements contain unknown errors, or our theoretical understanding is flawed. Physicists have scrutinized both methods exhaustively. The measurements appear solid. The theory must be incomplete. The tension has existed for years and keeps growing stronger as measurements improve. More data makes the disagreement more certain, not less. Scientists have proposed numerous explanations. Maybe dark energy behaves differently than assumed. Maybe neutrinos have unexpected properties. Maybe gravity works differently at cosmic scales. None of these ideas fully resolve the tension without creating new problems. But there is another possibility. What if the difference arises not from our theories or measurements, but from where we are measuring? What if our location inside a massive cosmic void distorts what we observe? Local measurements would reflect void dynamics. Early universe measurements would reflect average cosmic conditions. the two would naturally disagree. This explanation has gained serious attention because the void we inhabit is large enough and deep enough to create exactly the observed discrepancy. The void might be hiding in plain sight, masquerading as a crisis in cosmology. Gravity pulls matter together. This simple fact dominates cosmic evolution. But inside voids, gravity creates a paradox. With less matter present, gravitational attraction weakens. The void's interior pulls inward gently. The void's surroundings pull outward strongly. For galaxies caught inside, the outward pull wins. They accelerate away from the void's center toward its denser edges. This movement creates an illusion that confounds measurements of cosmic expansion. Picture a galaxy sitting in our void. The sparse matter inside the void pulls on it weakly. The massive shell of galaxy clusters surrounding the void pulls on it powerfully. The galaxy moves toward that shell, fleeing the emptiness. From our perspective, watching from inside the same void, this galaxy appears to recede faster than cosmic expansion alone would drive it. We interpret this as faster expansion. We calculate a higher Hubble constant. Our local measurements become biased. The effect compounds with distance. Galaxies farther from us feel stronger acceleration as they approach the void's edge where density gradients are steepest. Very distant galaxies, beyond void boundaries, experience normal cosmic expansion without the void's influence. Our local universe appears to expand faster than the distant universe. This matches exactly what astronomers observe. The Hubble tension could simply be void dynamics misinterpreted as cosmic acceleration. Indranil Banik, a cosmologist at the University of St. Andrews, led recent research quantifying this effect. His team calculated how matter flows in and around large voids. They modeled how these flows alter observations. For a void roughly 20% less dense than average, and roughly 1 billion light-years across, the distortion reaches precisely the magnitude needed to explain the Hubble tension. If we sit near the center of such a void, our measurements would overestimate the true cosmic expansion rate by about 9%. The agreement is remarkable. But the void creates other observable effects beyond just velocity measurements. Light traveling through voids experiences gravitational redshift differently than light traveling through normal regions. Photons lose energy, climbing out of gravitational wells. In voids, the wells are shallower. Less energy loss occurs. This subtle effect alters how we calculate distances from brightness measurements. The void influences multiple aspects of cosmological observations simultaneously. Time also behaves strangely. General relativity shows that gravity affects how fast time passes. Stronger gravity means slower time. In dense regions filled with matter, clocks tick more slowly than in empty regions. Over billions of years, this difference accumulates. Regions in voids may have aged more than regions in dense areas, even though both started from the same Big Bang. The concept challenges our assumption that the universe has a single age everywhere. Different regions may have different ages depending on their matter density history. These time differences affect how we interpret cosmic evolution. When we look at distant galaxies, we see them as they were billions of years ago. But how many billions? The answer depends on assumptions about how uniformly time has passed. If voids experience accelerated aging, our cosmic timelines need adjustment. The universe might be older in some places and younger in others. The implications grow more disorienting the deeper you examine them. Everything we thought we knew about measuring cosmic distances and ages may need recalibration if we truly inhabit a supervoid. Sound waves froze into the fabric of space. This statement sounds like fiction but describes real physics. In the universe's first few 100,000 years, matter existed as hot plasma. Pressure waves rippled through this plasma, moving at roughly half the speed of light. These waves were sound, traveling through a medium that filled all of existence. Then the universe cooled. Atoms formed. The plasma vanished. The sound waves stopped propagating, and became permanent features in how matter distributed across space. Today, we see these frozen sound waves as patterns in galaxy arrangements. Galaxies are slightly more likely to be separated by specific distances that correspond to how far the original sound waves traveled. These patterns are called baryon acoustic oscillations. Baryons are the protons and neutrons that make up normal matter. Acoustic means sound. Oscillations means waves. Together, the term describes sound waves in normal matter from the early universe. These oscillations provide a cosmic ruler. Because we know how far the waves traveled before freezing, we know the physical scale they represent. By measuring how large this scale appears at different distances, we can determine how the universe has expanded over time. It works like recognizing a meter stick and using it to judge distances and sizes of other objects. The oscillations act as standard rulers scattered throughout cosmic history. Indranil Banik and his team analyzed 20 years of baryon acoustic oscillation data. They compared two scenarios. First, a universe where matter distributes uniformly and we live in a typical location. Second, a universe where we inhabit a large void that distorts local observations. They calculated which scenario better matches the observed patterns. The result was stunning. The void model proved 100 million times more likely than the uniform model. 100 million is not a small factor. In statistics, even a factor of 100 makes a conclusion essentially certain. A factor of 1 million would be overwhelming. 100 million represents evidence so strong that maintaining skepticism becomes unreasonable. The data screams that we live in a void. Yet, many cosmologists remain reluctant to accept this conclusion because it violates cherished principles about our place in the cosmos. The baryon acoustic oscillations reveal subtle distortions in galaxy clustering that only a void can explain. In a uniform universe, the oscillation patterns should look identical in all directions and at all distances. Instead, patterns show systematic variations that match predictions for an underdense region. Galaxies in certain directions cluster slightly differently than galaxies in other directions. The differences align with void geometry. The data contains a signature that cannot be explained by random chance or measurement error. Additional confirmation comes from comparing different redshift ranges. Redshift measures how much light has been stretched by cosmic expansion, which correlates with distance and look-back time. Nearby observations should show stronger void effects than distant observations because distant observations see beyond the void. The data shows exactly this pattern. Local structure appears more irregular and sparse. Distant structure appears more uniform and typical. The transition occurs at roughly the distance where the void's edge should lie. Other research groups reach similar conclusions using different methods. Multiple independent analyses converge on the same answer. The evidence keeps accumulating, yet accepting the void means accepting that the cosmological principle, which states that no location in the universe should be special, does not hold at the largest observable scales. That principle has guided cosmology for nearly a century. Abandoning it requires extraordinary evidence. The evidence now qualifies as extraordinary. Imagine standing in a room. The walls, floor, and ceiling pull on you with gravitational attraction, but the room is mostly empty, so most pulling comes from beyond the room. Outside matter pulls you outward more strongly than inside matter pulls you inward. If the room were in space and gravity was the only force, you would drift toward the walls. Voids work this way at cosmic scales. Inside the Keenan-Barger-Cowie void, galaxies experience weak inward pull from the sparse interior matter and strong outward pull from the dense surrounding matter. The imbalance drives them outward. This outward motion is called peculiar velocity, meaning velocity that deviates from pure cosmic expansion. All galaxies have some peculiar velocity from local gravitational interactions. But void galaxies have systematically outward peculiar velocities. They flee the emptiness. This behavior inverts normal expectations. Usually, gravity pulls things together matter clumps, structures collapse and densify. In voids, the opposite occurs. Structures spread apart. The void empties further. It is not that gravity reverses, but that the dominant gravitational forces point outward rather than inward. The effect resembles how bubbles in boiling water expand as surrounding pressure pushes them larger. Astrophysicist Alice Pisani has studied void dynamics extensively. She created visualizations showing how matter flows around voids. In normal regions, arrows representing gravitational forces point inward toward dense clusters. In voids, arrows point outward toward the edges. Galaxies drift along these arrow paths over hundreds of millions of years. The local group, containing our Milky Way, is slowly moving outward through the void toward denser regions beyond. The outward flow has measurable consequences. Astronomers can detect peculiar velocities by comparing galaxy distances calculated from their brightness versus distances calculated from their redshift. Redshift includes both cosmic expansion and peculiar velocity. Brightness-based distance measures cosmic expansion alone. The difference reveals peculiar velocity. For galaxies in our void, this method consistently shows outward motion matching void model predictions. Another effect arises from reduced gravitational potential. Gravitational potential measures how deep the gravity well is at a location. Dense regions have deep wells. Light climbing out of these wells loses energy and becomes redshifted. Voids have shallow wells. Light experiences less gravitational redshift. This effect is tiny for individual photons, but accumulates over cosmic distances. Observations of distant objects seen through voids should show slightly different properties than observations through dense regions. Recent studies have found exactly such variations. Gravity also affects time, as Einstein showed. Stronger gravitational fields cause time to pass more slowly. An atomic clock in a dense galaxy cluster would tick slightly slower than an identical clock in a void galaxy. Over billions of years, this difference adds up. Regions in voids may have experienced more time than dense regions, even though both started simultaneously at the Big Bang. This means the void could actually be older, in a sense, than surrounding areas. The implications challenge the concept of a universal cosmic age. The weakened gravity in voids also affects how structures form. In normal regions, small density enhancements grow into galaxies and clusters efficiently. In voids, gravity is too weak to easily assemble large structures. Small dwarf galaxies can form, but giant elliptical galaxies are rare. The Milky Way is somewhat unusual for a void galaxy. Most void galaxies are smaller and dimmer. Our galaxy may have formed before the void fully developed, or it may have migrated into the void from denser surroundings. Either explanation suggests complicated dynamical history. Understanding how gravity operates differently in voids versus dense regions is essential for interpreting cosmological observations correctly. If we assume uniform gravity everywhere, we misunderstand what our measurements mean. Voids do not end abruptly. They transition gradually from underdense interiors to overdense boundaries. The transition zone forms a shell where matter concentrates. Think of soap bubbles. The interior is mostly air. The surface contains concentrated soapy film. Cosmic voids work similarly. Their boundaries become matter-rich regions where galaxy clusters accumulate. Our void has such a shell, and mapping it reveals cosmic architecture on the grandest scales. The shell begins roughly 700 million light-years from our position. At that distance, galaxy counts start increasing above average. Farther out, around 800 to 900 million light-years, density reaches and exceeds normal cosmic values. Beyond 1 billion light-years, the universe looks typical. The shell spans a thickness of 200 to 300 million light-years. Inside this shell, enormous galaxy superclusters dominate. These are some of the most massive structures in the observable universe. One notable structure in the shell is the Shapley supercluster. This monster contains over 8,000 galaxies. and has a mass equivalent to roughly 10,000 trillion times the mass of our galaxy. It sits approximately 650 million light-years away, right at the inner edge of the void's boundary shell. The Shapley supercluster pulls on everything around it with tremendous gravitational force. Our entire local group, including the Milky Way and Andromeda, is slowly drifting towards Shapley at roughly 600 kilometers per second. This motion illustrates void dynamics perfectly. We are not moving toward Shapley because it is particularly special compared to other superclusters. We move toward it because it is part of the dense shell surrounding our underdense void. The void pushes us outward. Shapley and structures like it pull us outward. Both effects point the same direction. The combination creates our peculiar velocity, which is among the largest known peculiar velocities for any galaxy group. The boundary shell also contains the Sloan Great Wall, one of the largest known structures in the universe. This immense chain of galaxy superclusters stretches over 1.3 billion light-years long. It forms part of the vast cosmic web, but specifically marks a transition from void to normal density. Multiple other massive structures populate the shell region, creating a ring of matter around the void. Why do shells form? The answer involves how voids grow. Initially, a region has slightly less matter than average. Gravity pulls matter from this region toward denser surroundings. As matter leaves, the region becomes even less dense, but the matter does not travel far. It accumulates at the void's edges, where it encounters matter from adjacent regions. These boundary zones become convergence points. Over billions of years, they evolve into the densest structures in the universe. The void feeds its own boundary, making the contrast between interior and exterior increasingly extreme. The shell geometry affects observations. When we look in different directions, we see through different path lengths of underdense and overdense regions. Some lines of sight pass mostly through void before hitting the shell. Others pass through the shell at different angles or distances. This creates asymmetries in what we observe. The universe should look uniform in all directions if we occupy a typical location. Instead, we see directional variations that match predictions for living inside a large void with a surrounding shell. Mapping the shell requires surveying millions of galaxies and calculating their distances accurately. Projects like the Sloan Digital Sky Survey have made this possible. The resulting three-dimensional maps clearly show the void and its boundary. Our location appears as a bubble of underdensity surrounded by walls of light representing galaxy concentrations. Living inside this shell gives us a distorted view of cosmic structure and expansion. Einstein discovered that time is not universal. Gravity warps time, causing it to pass at different rates depending on local gravitational strength. This is not science fiction. It is measured fact. Atomic clocks at different altitudes on Earth tick at different speeds. Satellites must correct for time dilation, or their navigation systems would fail. The effect is real, and at cosmic scales, it becomes profound. In regions of strong gravity, time slows down. Near a black hole, time can nearly stop relative to distant observers. In regions of weak gravity, time speeds up. Cosmic voids, with their sparse matter and weak gravitational fields, experience faster time flow than dense galaxy clusters. The difference is tiny moment to moment, but over billions of years, it accumulates. A clock that began ticking at the Big Bang would show different readings depending on whether it spent those billions of years in a void or in a dense region. Researchers estimate that atomic clocks in voids could tick up to 30% faster than clocks in dense clusters. Over 13.8 billion years. That means roughly 4 billion more years have effectively passed in voids compared to dense regions. This does not mean the void is older in the sense of existing longer. It means that more time has elapsed there, more cosmic expansion has occurred, more aging has happened. The concept strains intuition but follows directly from general relativity. This time, dilation affects how we interpret observations. When astronomers say the universe is 13.8 billion years old, they mean the time elapsed since the Big Bang as measured by a clock moving through average density regions. But we live in a below-average density region. More time may have passed here. The local universe could be older than we think, or at least have aged more. This affects calculations of distances, expansion rates, and structure formation timescales. The timescape cosmology model, developed by David Wiltshire and colleagues, takes these effects seriously. Instead of assuming the universe has a single age and expansion rate everywhere, this model calculates how time differences and expansion differences arise from the lumpy distribution of matter. In timescape cosmology, voids expand faster than average because more time passes in them. Dense regions expand slower because less time passes. When averaged appropriately, these differences can explain accelerated expansion without needing dark energy. Recent analyses of Type 1 a supernovae data tested timescape predictions against standard cosmology. The supernovae act as standard candles, allowing distance measurements. When researchers analyzed over 1,500 supernovae using timescape assumptions, the model fit the data better than standard dark energy models. This does not prove timescape is correct, but it demonstrates the idea is viable. The universe's apparent acceleration might be an artifact of averaging observations from regions where time has passed at different rates. Critics argue that time dilation effects are too small to matter cosmologically. Supporters counter that over billions of years and across billions of light years, small effects become large. The debate continues, but the underlying physics is sound. Time does move faster in voids. The question is whether this fact explains major cosmological puzzles or is merely a minor correction. If timescape cosmology is right, then our void environment has given us a warped perspective on cosmic history. We measure time and expansion from a location where both proceed faster than average. Our calculations reflect this unusual vantage point. Correcting for our location would change our understanding of the universe's age, expansion history, and ultimate fate. The void would not just be a large, empty region. It would be a temporal anomaly skewing everything we observe. Every measurement we make assumes time flows uniformly everywhere. That assumption might be catastrophically wrong. Modern cosmology rests on a framework called lambda cold dark matter. Cosmologists abbreviate it as LCDM. This model describes how the universe evolved from the Big Bang to today. It includes ordinary matter, cold, dark matter that does not emit light, and dark energy represented by lambda that drives accelerated expansion. The model works spectacularly well in most situations. It explains the cosmic microwave background patterns. It predicts large-scale structure formation. It accounts for the abundance of light elements. It is cosmology's standard model, but LCDM struggles with the Keenan-Barger-Cowie void. The model predicts that structures of certain sizes should be common, while structures of other sizes should be rare. Voids roughly 100 to 300 million light-years across fit LCDM predictions comfortably. Voids approaching or exceeding 1 billion light-years should be extraordinarily uncommon. The probability of such large, deep voids forming through random density fluctuations is vanishingly small. Yet, we observe ourselves in exactly such a void. Moritz Hasselbauer, Indranil Banik, and Pavel Krupa quantified this problem using simulations. They used the Millennium XXL simulation, one of the largest and most sophisticated LCDM simulations ever run. It simulates a cosmic volume large enough to contain many voids and allows statistical analysis. The team searched through this simulated universe for voids matching the observed properties of the KBC void in size, depth, and density profile. They found none that compared. The probability calculation is damning. The simulations show that voids like ours should occur in less than 1 in 10,000 similar cosmic volumes. Combine this with the Hubble tension, and the tension with LCDM reaches 7 standard deviations. In statistical terms, 7 standard deviations means the probability of the result occurring by chance is roughly 1 in 1 trillion. No competent scientist accepts a theory that produces 1 in 1 trillion events routinely. Something is wrong with LCDM. Either the model underestimates how often large voids form, or our void is not actually as unusual as it appears, or the model is missing fundamental physics. The first option requires tweaking how structures grow in simulations. The second option requires showing our measurements are biased. The third option requires new physics. None are palatable to theorists who spent decades developing and testing LCDM. Alternative theories are being explored. One possibility involves modified Newtonian dynamics, abbreviated MOND. This theory proposes that gravity works differently than Newton and Einstein described, when gravitational acceleration becomes extremely weak. Such weak accelerations occur at the edges of galaxies and in the vast spaces between galaxy clusters. MOND was originally developed to explain galaxy rotation curves without dark matter. But MOND also predicts that large-scale structures should grow faster than LCDM expects. In MOND, voids as large as the KBC void form, naturally and commonly. Hasbauer and colleagues ran cosmological simulations using MOND instead of LCDM. They found that the KBC void and the Hubble tension both emerged naturally in MOND cosmology. The void is not an anomaly, but a normal feature. The theory that struggles to produce the void is LCDM. The theory that comfortably produces it is MOND. This does not prove MOND is correct, but it shows the standard model is incomplete. Either dark matter behaves differently than assumed, or gravity behaves differently than assumed, or both. There are other strange observations that LCDM handles poorly. Massive galaxy clusters at high redshifts appear earlier in cosmic history than simulations predict. Large ring-like structures of galaxies span distances that should not yet have formed when we observe them. Dwarf galaxies in voids are rarer than simulations predict. Each discrepancy individually might be explainable. Together, they suggest systematic problems with the model's treatment of structure formation. The scientific method requires abandoning theories that make consistently wrong predictions. LCDM is not there yet, but it is struggling. The KBC void may be the most problematic observation because it is so extreme and well confirmed. Ignoring it is not an option. Gravity weakens with distance. Newton showed this in the 1600s. Einstein refined it in the early 1900s. Both formulations agree that gravity falls off as the inverse square of distance. Double the distance, gravity weakens by a factor of 4. This relationship has been tested extensively and holds in the solar system, near Earth, and around stars. But what about at the enormous distances between galaxies? What about in the weak gravitational fields of cosmic voids? Mordechai Milgrom proposed in 1983 that gravity might behave differently when acceleration becomes extremely small. His theory, called modified Newtonian dynamics, or MOND, suggests that below a certain acceleration threshold, gravity weakens less rapidly than Newton predicted. This makes gravity slightly stronger at very large distances than standard physics expects. The threshold acceleration is tiny, about 1/10 billionth the acceleration you feel from Earth's gravity. You never experience accelerations that small in daily life, but galaxies orbiting in their outskirts do. Galaxy clusters interacting across vast distances do. Cosmic voids expanding outward do. MOND was developed to explain galaxy rotation curves. Stars orbiting far from galaxy centers move faster than Newtonian gravity predicts based on visible matter. Cosmologists explain this with dark matter, invisible mass that provides extra gravity. MOND explains it by saying gravity works differently at those distances. Both explanations fit the galaxy rotation data, but they make different predictions for other situations. One key difference involves structure formation on cosmic scales. In standard cosmology, with dark matter, structures grow through gravitational collapse. Denser regions pull in surrounding matter, but the rate of growth is limited by how quickly matter can fall inward. In MOND, gravity is slightly stronger at large distances, so matter falls inward faster. structures grow more efficiently. This means large structures should form earlier and more easily in MON-D than in LCDM. It also means voids should empty out more efficiently, becoming deeper and larger than LCDM predicts. Pavel Krupa and colleagues applied MOND to cosmological simulations. They found that MOND naturally produces voids similar in size and depth to the KBC void. These voids are not rare anomalies, but normal features of cosmic structure in MOND. The reason is that the enhanced gravity at large scales accelerates both collapse in dense regions and evacuation in underdense regions. The void empties faster because surrounding dense regions pull matter out more efficiently. The contrast between voids and filaments becomes more extreme than in standard cosmology. MOND also explains the Hubble tension naturally in the context of a large void. In LCDM, the void is so improbable that using it to explain the Hubble tension feels like special pleading. In MOND, the void is expected, so explaining observations through void dynamics is reasonable. The outflow from a MOND void creates exactly the observed local expansion rate excess. The theory makes a prediction, and observation confirms it. This is how successful physics works. But MOND faces serious challenges. It struggles to explain the cosmic microwave background without some form of dark matter. It has difficulty with gravitational lensing observations that show matter distributions inconsistent with MOND predictions. Some galaxy clusters appear to contain more mass than visible matter plus MOND modifications can account for. To address these issues, MOND cosmologists propose that a small amount of dark matter in the form of sterile neutrinos might exist alongside modified gravity. This hybrid model, sometimes called NuHDM for neutrino hot dark matter, can fit most observations. Whether MOND is the correct alternative to LCDM remains uncertain, but the theory demonstrates that alternatives exist. LCDM is not the only possible explanation for what we observe. If LCDM consistently fails to explain large-scale structures like the KBC void, science demands considering alternatives seriously. The standard model may not be standard much longer. You live inside Laniakea. This Hawaiian word means immeasurable heaven, an appropriate name for one of the largest structures containing our galaxy. Laniakea is a supercluster, a collection of galaxy groups and clusters bound by their mutual gravity and moving together through the cosmos. It spans 520 million light-years across and contains the mass of roughly 100,000 galaxies like the Milky Way. For decades, astronomers thought the Virgo supercluster contained our galaxy. Virgo is a prominent cluster of galaxies about 53 million light-years away, and it seemed to anchor our local cosmic neighborhood. But in 2014, researchers using new mapping techniques realized the structure is larger. Virgo is merely one component of the grander Laniakea supercluster. The Milky Way sits near the outer edge of Laniakea, in a relatively sparse region. This makes sense now, given the void. Laniakea itself exists entirely within the KBC void. This fact is crucial, but often overlooked. The supercluster is not outside the void looking in. It is inside the void, part of the underdense region. Laniakea represents one of the denser concentrations within the void, but its average density still falls below cosmic average. The void is so large that it contains multiple superclusters, each massive yet still contributing to overall underdensity. The supercluster's structure reveals void dynamics. Laniakea has a central region called the Great Attractor, an area of enhanced gravity toward which nearby galaxies flow. But Laniakea, as a whole, moves toward the even larger Shapley supercluster outside the void. The entire supercluster is being pulled outward, fleeing the void toward denser surroundings. We are passengers on a cosmic structure in motion, drifting through the void toward its boundary. Mapping Laniakea required understanding peculiar velocities. Galaxies do not just move with cosmic expansion, they also move due to gravitational attraction from nearby structures. By measuring these peculiar velocities for thousands of galaxies, researchers traced the flows of matter. They identified regions acting as sources, pushing matter away, and sinks, pulling matter in. Laniakea emerged as a basin of attraction, a region where matter flows inward toward the great attractor. But this basin sits within the larger outflow pattern of the void. The discovery of Laniakea changed how we understand our cosmic address. Previously, addresses would list Earth, Solar System, Milky Way Galaxy, Local Group, Virgo Supercluster. Now we add Laniakea Supercluster, but we must also add KBC Void. Our address is more complex than thought. We belong to nested structures, each providing context for the others. The void provides the largest context visible in current surveys. Laniakea's fate is tied to the void's evolution. As the void continues expanding, driven by dark energy, Laniakea will stretch and thin. Eventually, the supercluster may dissipate as its member galaxies spread apart. Some may be pulled out of Laniakea entirely by stronger attractions beyond the void. In tens of billions of years, structures like Laniakea may cease to exist as bound entities. The void will consume them. Understanding Laniakea also illuminates how structure forms hierarchically. Small galaxies merge into larger galaxies. Galaxies group into clusters. Clusters align into superclusters. Superclusters organize around and within voids. Each level of structure emerges from and influences the next. The cosmic web is fractal-like, showing similar patterns at different scales. Our position within this hierarchy is unusual because we sit in an underdense branch of the fractal rather than an overdense one. The realization that Laniakea sits inside the void rather than outside it surprised many astronomers. It seems counterintuitive that such a massive structure could exist in an underdense region. But voids are not absolutely empty. They are relatively empty. Laniakea proves that even within voids, gravity can assemble impressive structures. They are just less common and less massive than structures in normal density regions. Living in Laniakea inside the KBC void gives us a doubly unusual cosmic address. The universe began remarkably smooth. Immediately after the Big Bang, matter and energy spread nearly uniformly in all directions. Temperature varied by less than 1 part in 100,000 from place to place. No galaxies existed, no stars shone, just hot plasma filling all of space, expanding and cooling. Yet within this smooth beginning, tiny irregularities existed. Quantum fluctuations during the inflationary period created microscopic density variations. Some regions had slightly more matter, some had slightly less. These differences were random, like noise, with no preferred pattern. Gravity amplified the noise. Regions with extra matter pulled in surrounding material. As they gained mass, their gravitational pull strengthened. They attracted even more matter. The rich got richer through this positive feedback loop. Meanwhile, regions with less matter lost material to their denser neighbors. As matter left, these regions became less able to hold on to remaining matter. They emptied progressively. The poor got poorer. Over hundreds of millions of years, tiny fluctuations grew into dramatic differences. The first structures to form were small. Dwarf galaxies assembled when the universe was only a few 100 million years old. These merged into larger galaxies over time. Galaxies clustered together into groups, then into clusters. The largest structures took billions of years to develop, but voids formed as the negative image of this process. Wherever matter collapsed into galaxies and clusters, it was pulled from somewhere. Those somewhere locations became voids. Think of the universe as an expanding sponge. As the sponge grows, the solid material concentrates into strands, while bubbles form between them. The cosmic web works similarly. Gravity sculpts matter into filaments and nodes while leaving empty bubbles. The bubbles are voids. They are not carved out by some external force. They form naturally as matter redistributes itself according to gravity's dictates. Initial density variations determined void locations. Regions that started even slightly underdense became voids. Regions that started overdense became filaments and clusters. The transition happened gradually over billions of years. Early voids were smaller and less empty than today's voids. They have grown and deepened with time. As the universe expanded, voids expanded faster than average because their weak internal gravity could not resist expansion effectively. Dense regions expanded slower because gravity partially counteracted expansion. The KBC void formed from a particularly large, underdense region in the early universe. Perhaps it was a rare statistical fluctuation, a region where several small underdensities overlapped. Perhaps it formed near a larger scale feature that channeled matter away. The exact origin is unclear. What is clear is that by the time galaxies were forming, this region already contained less matter than average. As galaxies assembled, they preferentially formed along the void's edges where matter was denser. The void's interior remained sparse. Our Milky Way formed before the void fully developed. The galaxy is roughly 13 billion years old, meaning it assembled when the universe was less than 1 billion years old. At that time, the KBC void was smaller and less pronounced. The Milky Way may have formed in what would eventually become void territory, or it may have migrated into the void as structures evolved. Galaxy motions over billions of years can transport them considerable distances. The local group's current trajectory toward Shapley suggests we are still migrating, still responding to the density gradients established by ancient density fluctuations. Voids continue evolving today. They expand as dark energy drives cosmic acceleration. Their interiors empty further as remaining matter drifts toward boundaries. In the distant future, voids will dominate the universe's volume even more than they do now. The process that began with tiny quantum fluctuations will culminate in a cosmos mostly devoid of matter, with isolated islands of galaxies separated by incomprehensible emptiness. We are witnessing the universe midway through this transformation. Dark energy is the universe's most mysterious component. It accounts for roughly 68% of the cosmic energy budget, yet remains completely unexplained by physics. Dark energy causes cosmic expansion to accelerate rather than slow down. Gravity should pull the universe back together, decelerating expansion. Instead, expansion speeds up. Astronomers discovered this in the late 1990s by observing distant supernovae. The discovery won a Nobel Prize and created one of physics' deepest puzzles. Dark energy affects different parts of the universe differently. In dense regions like galaxy clusters, gravity is strong enough to resist dark energy completely. Clusters hold together despite accelerating expansion. Galaxies within clusters orbit each other. Stars within galaxies orbit galactic centers. Dark energy does not disrupt these bound systems. But in voids, gravity is too weak to resist. Dark energy dominates completely. Voids expand faster than the universe's average expansion rate. They grow more rapidly than any other large-scale structures. Imagine a balloon with coins glued to its surface. As you inflate the balloon, the surface expands, but the coins do not grow. The gaps between coins increase, while the coins themselves remain constant. The cosmos works similarly. Galaxy clusters are like coins, held together by gravity. The spaces between them, the voids, are like the balloon surface. They expand with cosmic acceleration while dense structures resist. This differential expansion has profound consequences. Voids that were already large become enormous. The volume of space occupied by voids increases faster than the volume occupied by matter. Today, voids make up about 80% of the universe by volume. In the future, they will constitute an even larger fraction. The universe becomes progressively emptier as voids grow and dense structures become more isolated. The KBC void is expanding. Measurements of galaxy velocities confirm this. Galaxies near the void's center move outward faster than pure cosmic expansion would drive them. This excess velocity comes from the combination of dark energy's effect and the outward gravitational pull from surrounding dense matter. The void behaves like an expanding bubble, pushing its boundaries outward and growing larger with time. Dark energy's equation of state determines how strongly it drives expansion. Current measurements suggest dark energy has constant density even as space expands. This creates continuously accelerating expansion. But some theories predict dark energy could weaken or strengthen over time. If it weakens, expansion might eventually slow or reverse. If it strengthens, expansion could accelerate catastrophically, tearing apart all structures in a Big Rip scenario. Observations of how voids evolve provide clues about dark energy's properties. Studies have attempted to use void expansion rates to constrain dark energy models. The idea is that voids respond more sensitively to dark energy than dense regions because gravity does not interfere. By measuring how fast different voids expand at different cosmic epochs, researchers can test whether dark energy is changing. So far, results suggest dark energy has remained roughly constant over the last several billion years, but uncertainties are large and more data is needed. Some theories propose that dark energy emerges from voids rather than being a fundamental property of space. In this view, the expansion of voids generates a kind of pressure that pushes space apart. The more voids exist and the larger they grow, the stronger this effect becomes. This could explain why cosmic acceleration began roughly 5 billion years ago rather than earlier. Perhaps that is when voids had grown large enough to dominate the universe's expansion dynamics. The theory remains speculative but offers a concrete mechanism for dark energy rather than treating it as pure mystery. If voids generate dark energy through their expansion dynamics, then living in a large void would place us at the source of cosmic acceleration. We would be inside one of the engines driving the universe's fate. The void would not just affect our local measurements, it would represent a fundamental component of cosmic evolution. Understanding voids would become essential for understanding the universe itself. Voids are where dark energy wins its ultimate victory over gravity. Space is mostly nothing. This statement sounds obvious but conceals a profound asymmetry. When you look at images of the universe, they show galaxies, nebulae, and bright structures. These images mislead you. They capture the rare places where matter concentrates. The vast majority of cosmic volume contains almost nothing. Voids dominate the universe's geography overwhelmingly. Surveys measuring three-dimensional positions of millions of galaxies reveal the true picture. Researchers calculate volumes occupied by dense filaments and clusters versus volumes occupied by voids. The numbers are stark. Voids account for roughly 80 to 85% of all space. Dense structures occupy 15 to 20%. Yet these percentages reverse when measuring mass. Dense regions contain 90% of normal matter. Voids contain only 10%. The universe is mostly empty, but its mass concentrates in small regions. This imbalance creates unusual dynamics. Imagine a city where 80% of land area is empty parks, but 90% of population lives in buildings covering 20% of area. The parks would seem vast and empty. The buildings would seem crowded and dense. The contrast would dominate city planning and dynamics. Cosmic structure works similarly. Voids are enormous but irrelevant for most gravitational interactions. Dense regions are small but dominate gravity. The imbalance also affects observations. When astronomers measure average cosmic density, they count all the matter and divide by total volume. This gives the mean density, but almost nowhere actually has this mean density. Dense regions have density far above average. Voids have density far below average. The mean is a mathematical abstraction not corresponding to typical locations. Most of space is much emptier than the mean suggests. Most matter resides in places much denser than the mean. Living in a void means occupying the majority environment by volume, but the minority environment by mass. If you randomly placed an observer in the universe without regard to where matter is, they would most likely land in a void. But if you placed an observer near a randomly selected atom, they would most likely be in a dense region. These two procedures give opposite answers about what is typical. The question becomes which procedure better represents reality. The cosmological principle assumes that on large scales, the universe is homogeneous. No location should be special, but this principle refers to averaging over large volumes. Within those volumes, voids and dense regions coexist. The principle does not say every location experiences average density. It says the average of many locations equals the cosmic mean. We happen to occupy one of the many below-average locations. Some scientists argue that living in a void violates the spirit of the cosmological principle, even if it does not violate the letter. They feel uncomfortable with the idea that our measurements might be biased by our location. They prefer theories where observations match predictions, assuming typical conditions. But nature does not care about our preferences. If we live in a void, we must account for it. The 80% figure also applies to the future. As voids expand faster than dense regions, they will occupy progressively more volume. Eventually, voids might constitute 90 or 95% of space. Dense structures will become increasingly isolated, separated by incomprehensible distances. The universe will resemble a few grains of sand scattered across the Sahara Desert. Each grain represents a galaxy cluster. The desert represents void. This future already begins around us. The KBC void is not unique. Many large voids exist throughout the observable universe. Each grows, each empties. Together, they are transforming the cosmos into mostly nothingness, punctuated by rare islands of matter. We witness this transformation from inside one of the emptier islands. The universe is dying by expansion into emptiness. What if dark energy does not exist? This question seems absurd given that accelerating expansion is observed. But what if the acceleration is not caused by a mysterious force, but by ordinary gravity operating in a lumpy universe? What if voids are the answer? Standard cosmology assumes the universe expands uniformly. Every cubic meter of space stretches at the same rate as every other cubic meter. This assumption simplifies calculations enormously. It allows treating the universe as a smooth fluid rather than tracking individual structures. But the assumption is clearly wrong at small scales. Galaxies do not expand. Solar systems do not expand. Even galaxy clusters resist expansion. Only the spaces between clusters expand. The universe is not smooth. Treating expansion as uniform when it actually varies could introduce errors in how we interpret observations. These errors might accumulate to make cosmic expansion appear accelerated when it actually is not. Several alternative theories explore this possibility. The most developed is timescape cosmology, which we discussed earlier. Another approach examines how voids create backreaction on cosmic expansion. Backreaction refers to how small-scale inhomogeneities affect large-scale average properties. Imagine ocean waves. Locally, water moves up and down in complex patterns. But averaged over large areas, the ocean has a mean height and a mean energy density. The averaging process is not trivial, though. Sometimes, the average of the squares does not equal the square of the average. Nonlinear effects can create discrepancies. Similar issues arise in cosmology. Voids expand faster than average. Dense regions expand slower than average. When you average these regions to calculate the universe's mean expansion rate, you must weight them properly. If you weight by volume, voids dominate because they occupy more space. If you weight by mass, dense regions dominate because they contain more matter. Different weighting schemes give different answers for the average expansion rate. Some calculations suggest that proper averaging could explain observed acceleration without dark energy. Critics of backreaction models argue that the effects are too small to explain the observed acceleration magnitude. They claim that while inhomogeneities do affect expansion, the effect amounts to only a few %, not the large acceleration observed. Defenders counter that the critics make unjustified assumptions about how to perform the averaging. The debate remains unresolved technically. A different possibility is that voids themselves generate something resembling dark energy through their dynamics. As voids expand, they create pressure on surrounding structures. This pressure pushes galaxies apart, mimicking accelerated expansion. If voids dominate cosmic volume, their cumulative pressure could drive observed acceleration. Recent papers have explored this mechanism mathematically. The calculations show that void pressure can produce acceleration matching observations under certain conditions. Yet another idea involves how time passes differently in voids versus dense regions. If we measure cosmic expansion from a void where time runs faster, we will calculate faster expansion than observers in dense regions would calculate. The universe's actual expansion might be constant, but our perception of it from a time-dilated void makes it appear accelerated. This explanation requires no new physics, only proper application of general relativity in an inhomogeneous universe. All these alternatives share a common theme. They attempt to explain observations without invoking dark energy as a fundamental component of nature. Instead, they attribute observed phenomena to structure and gravity. Dark energy becomes an illusion created by averaging over an irregular universe from an irregular location. The universe does not contain mysterious energy driving acceleration. It contains voids, and voids create phenomena that resemble acceleration. If any of these alternatives proves correct, it will revolutionize cosmology. Dark energy would be demoted from fundamental mystery to accounting error. The KBC void would transform from curious anomaly to crucial clue. Our location inside the void would become central to understanding cosmic dynamics rather than an embarrassing violation of assumed uniformity. The void might not just affect our measurements. It might explain the biggest puzzle in cosmology. 3 galaxies dominate our immediate neighborhood. The Milky Way contains roughly 200 billion stars. Andromeda, slightly larger, holds perhaps 400 billion stars. Triangulum, much smaller, has 40 billion stars. Together with about 80 smaller dwarf galaxies, these form the local group. This collection of galaxies moves through space as a unit, bound by mutual gravity, and it sits in a very unusual place. The local group resides roughly 200 to 400 million light-years from the KBC void center, not at the center, not far from the center, but in an intermediate position that raises questions. If the void formed from random density fluctuations, the Milky Way could be anywhere within it. Finding ourselves offset from center by several 100 million light-years seems unremarkable at first. But combined with other factors, the position becomes puzzling. For one thing, we are close enough to the center to experience strong void effects. If we were near the void's edge, local expansion would appear more normal. Dense structures beyond the boundary would dominate our gravitational environment, but we are deep enough inside that the void's dynamics control what we observe. This amplifies any biases in our cosmological measurements. A location near the void center maximizes these biases. Additionally, the void appears roughly spherical with us near its center. This symmetry seems suspicious. In a truly random distribution, voids have irregular shapes. They elongate along certain axes. They merge with neighboring voids, creating complex geometries. The KBC void shows some asymmetries, certainly, but it is remarkably close to spherical, and we sit close to that sphere's center. What are the odds? Some researchers argue this is a selection effect. We can only discover voids we live inside. Since observers must exist where galaxies form, and galaxies are rarer in void centers, observers should typically find themselves offset from true centers. We should live in moderately underdense regions within voids, not the emptiest cores. Our position fits this expectation. The void appears centered on us because we are defining it based on observations from our location. Others counter that the selection effect is not strong enough to explain the data. The baryon acoustic oscillation measurements show structure that does not depend on where we define the center. The density profile is a physical fact, not an observational artifact. We genuinely appear to sit near the center of a genuine spherical underdensity. This needs explanation beyond selection effects. The local group's motion also seems unusual. We travel toward the Shapley supercluster at roughly 600 kilometers per second. This is one of the largest peculiar velocities measured for any galaxy group. It suggests strong gravitational influence from Shapley and weak resistance from our local environment. Both make sense if we are in a void. The void provides little gravitational anchor. Shapley pulls us strongly from beyond the void's boundary. Our trajectory points directly out of the void toward denser regions. In 10 billion years, if these motions continue, the local group will exit the KBC void entirely. We will enter the shell of dense matter surrounding the void. Our gravitational environment will change dramatically. Instead of isolated emptiness, we will find ourselves in a crowded supercluster region with many neighbors. The contrast will be profound, but 10 billion years is a long time. Stars will age, galaxies will evolve, the Milky Way and Andromeda will collide and merge into a single larger galaxy. By the time we exit the void, our cosmic address will have changed in multiple ways. The concept of the local group may not even apply after the galaxies merge. For now, though, we remain in the unusual position of living deep inside the largest void ever detected. Not at its heart, but close. Not typical for the universe, but maybe typical for observers. The position influences everything we measure about cosmic expansion and structure. Whether that influence can fully explain cosmological puzzles remains the crucial unanswered question. Our address determines our perspective on the universe. Galaxy clusters are the largest gravitationally bound structures. They contain hundreds to thousands of galaxies, along with vast amounts of hot gas and dark matter. The total mass reaches hundreds of trillions of times greater than our galaxy. These clusters do not form randomly. They mark the nodes in the cosmic web where filaments intersect, and their movements reveal how gravity shapes space on the grandest scales. Clusters inside voids move differently than clusters in normal regions. The difference lies in what pulls on them. A cluster in a dense region experiences gravity from all directions as surrounding structures tug it various ways. These forces partially cancel, leaving the cluster in approximate equilibrium. A cluster in a void experiences weak pull inward from the void's sparse interior and strong pull outward from the dense shells surrounding the void. The outward pull dominates. The cluster accelerates outward. Benjamin Hoschert measured this effect using the kinematic effect on cosmic microwave background radiation. As background photons pass through moving clusters, the photons shift in energy. The shift reveals the cluster's velocity. Hoschert analyzed dozens of clusters in our cosmic neighborhood. He found their velocity patterns match predictions for a void. Clusters show systematic outward motion away from our region toward denser surroundings. The velocities are not small. Typical peculiar velocities reach several hundred kilometers per second. The Great Attractor, a massive concentration of galaxies, pulls local clusters at over 600 kilometers per second. But the Great Attractor itself moves toward the Shapley supercluster. Everything flows outward from the void toward the densest nearby structure outside it. The pattern is unmistakable once you know to look for it. Another revealing measurement involves cluster masses. Clusters in voids should be less massive on average than clusters in normal regions, because forming massive structures requires abundant nearby matter. Voids provide less matter, so they produce smaller clusters. Surveys confirm this prediction. The largest clusters in the universe, those exceeding 10,000 trillion times our galaxy's mass, exist in dense regions, not voids. Our neighborhood lacks such monsters. The Virgo cluster, our closest major cluster, contains only about 1,200 galaxies. Nearby rich clusters in other regions contain several times more. The Coma cluster, roughly 320 million light-years away, holds over 1,000 galaxies in a much more compact volume than Virgo occupies. These comparisons suggest our region is genuinely underdense and has been for billions of years. Structures here never grew as large as structures elsewhere. Gravitational lensing provides independent confirmation. Massive clusters bend light from background galaxies, creating distorted images. The amount of distortion depends on the cluster's total mass. By measuring lensing for many clusters, astronomers map the mass distribution across the universe. These maps show that our region contains less mass than average, consistent with void predictions. The lensing data agrees with galaxy counts and velocity measurements. Multiple independent methods converge on the same conclusion. Some clusters show particularly strong lensing because they sit along our line of sight to even more distant structures. These foreground clusters magnify background galaxies, allowing detailed study of extremely distant objects. Interestingly, some of the strongest lensing clusters lie near the KBC void's boundary. These boundary clusters contain enormous mass concentrated in relatively small volumes. They represent the shell material surrounding the void. Their existence and positions fit void models well. The distribution of clusters also matters. In normal regions, clusters are separated by typical distances of roughly 100 to 200 million light-years. In our region, separations average larger. We have fewer clusters per unit volume, and those we have are more widely spaced. This is exactly what a void predicts. The cosmic web is sparser here. The gaps between nodes are wider. Galaxy clusters are lighthouses, illuminating cosmic structure. Their properties and motions tell us about the environment they inhabit. Everything about clusters in our neighborhood indicates we live in an underdense region. The evidence is not subtle. It is obvious once analyzed properly. The question is why it took so long to recognize. Nicolaus Copernicus taught humanity a humbling lesson. Earth is not the center of the universe. It orbits an ordinary star in an ordinary galaxy in an ordinary part of space. Nothing about our location is special. This idea became the cosmological principle, a foundational assumption in modern cosmology. The principle states that on large enough scales, the universe looks the same everywhere. No location is privileged. No observer has a unique view. All perspectives are equivalent. The principle guided cosmology for nearly a century. It justified treating the universe as homogeneous and isotropic in models and calculations. It allowed averaging over irregularities to extract mean properties. It meant observations from Earth could be generalized to the entire cosmos. The principle was more than a scientific hypothesis. It was a philosophical stance about humanity's place in nature. The KBC void challenges this principle directly. We do not occupy a typical location. We inhabit an unusually empty region, 7 times larger than average voids. Our view of the universe is biased by this environment. Observations from our position do not straightforwardly represent universal properties. We have a perspective that differs systematically from observers in normal density regions. Our location is special in ways Copernicus would find disturbing. Does this mean the cosmological principle is wrong? The answer depends on interpretation. Strictly speaking, the principle only claims uniformity on sufficiently large scales. It allows for variations at smaller scales. Voids and dense regions can exist as long as they average out over large volumes. A void 1 billion light-years across might still be considered a small-scale fluctuation if the relevant scale is tens of billions of light-years. By this interpretation, the principle survives, but this feels like evasion. A structure large enough to contain 100,000 galaxies is not a minor fluctuation. A density contrast that persists over 1 billion light-years is not a small-scale irregularity. The void is large compared to all but the most extreme distance scales. It is comparable to the size of the observable universe's typical large structures. Calling it a minor deviation from uniformity strains credibility. Another defense of the principle notes that other voids exist throughout the universe. We are not unique in inhabiting a void. Perhaps 20 or 30% of observers live in significant voids. If we are part of a substantial minority rather than a tiny anomaly, maybe the principle holds statistically. Different observers see different local environments, but averaged over all observers, the universe appears uniform. This defense also seems weak. If a significant fraction of observers occupy unusual environments that bias their measurements, those observers cannot trust their measurements to represent universal properties. They must correct for their location before drawing conclusions. This requires knowing they are in an unusual environment and understanding how it affects observations. Until recently, we did not know we were in a void. Our conclusions about cosmology were based on uncorrected, biased observations. How many other biases might we be unaware of? The deepest issue is philosophical. The cosmological principle embodies the idea that humans do not occupy a special place, but special compared to what? If the universe is genuinely irregular on large scales, some places must be denser and some emptier. Observers can exist in both types of locations. There is no objective standard for typical. The concept of being special becomes meaningless. Perhaps we should abandon the principle entirely and simply describe the universe as we find it, irregular and lumpy, without demanding that we occupy an average position within it. Some cosmologists embrace this view. They argue that the principle was always more assumption than evidence. It made calculations tractable, but was not observationally justified. As surveys improve and reveal more structure, irregularities keep appearing at larger scales. Perhaps the universe never becomes truly uniform, no matter how large a volume you average over. Perhaps there is no scale where the cosmological principle applies. If the principle fails, cosmology must be rebuilt on different foundations. Models assuming uniformity would need revision. Observations would require careful interpretation based on local environment. Predictions about distant regions could not rely on assuming those regions resemble our neighborhood. The entire framework of cosmology would shift from simple elegance to messy complexity. The void is forcing this reckoning. We can no longer pretend our location does not matter. Science progresses through better measurements. Theories rise and fall based on whether observations support them. The question of whether we live in a significant void and whether it explains cosmological puzzles cannot remain speculative forever. Upcoming observations will decide. Multiple independent tests are possible, and all are being pursued. Cosmic chronometers are one key test. These are galaxies that stopped forming stars long ago. Their stellar populations age predictably like clocks. By comparing the age of these galaxies at different redshifts, astronomers can reconstruct how the universe expanded over time. If we live in a void, local cosmic chronometers should show faster expansion than distant ones. The transition should occur at the void's boundary. Preliminary data exists, but more is needed for definitive conclusions. Projects targeting this measurement are underway. Baryon acoustic oscillations provide another test. We have 20 years of data, which supported the void hypothesis strongly. But data from more distant regions could reveal whether the underdensity is localized or extends even farther. If it is truly localized, oscillation patterns beyond 1 billion light-years should return to normal. If patterns remain irregular at larger distances, the void might be even bigger than thought, or our understanding of large-scale structure might be fundamentally flawed. Ongoing surveys will provide this data. Gravitational wave detectors add a new tool. Colliding black holes and neutron stars produce gravitational waves that travel through the universe. These waves carry information about distances independent of light. By measuring gravitational wave sources at various distances, astronomers can check whether distance measurements agree with electromagnetic observations. If the void distorts light-based measurements but not gravitational wave measurements, discrepancies will appear. Facilities like LIGO, Virgo, and the planned Einstein telescope will make these measurements possible. Direct imaging of void structure also continues improving. The Dark Energy Survey and its successors map galaxies in 3 dimensions with increasing precision. These surveys will define the void's boundaries more accurately. They will measure its density profile in detail. They will check whether it is truly spherical or has hidden asymmetries. Each refined measurement either strengthens or weakens the void hypothesis. Ambiguity will decrease as data accumulates. Type 1a supernovae remain crucial. These standard candles allowed the original discovery of accelerated expansion. More supernovae at various distances will refine expansion history measurements. If local expansion rates differ from distant rates by amounts matching void predictions, the void gains support. If no such difference appears, the void cannot explain the Hubble tension. Dedicated supernova surveys continue collecting data. Cosmic microwave background measurements also matter. The void should create subtle patterns in the background radiation as photons pass through the underdense region. These patterns, called the integrated effect, have been tentatively detected but require confirmation. Future space missions with improved sensitivity could definitively measure these patterns and compare them to void model predictions. Computer simulations provide theoretical predictions to test against observations. As simulations become more sophisticated, they can explore what void universes look like in detail. Different cosmological models predict different void properties. By comparing observed void properties to simulated possibilities, researchers can determine which models are viable. If no standard model simulation produces voids like ours, alternatives like MOND gain credibility. The timeline for these measurements spans the next 10 to 20 years. Some data will arrive soon. Other data requires missions not yet launched, but within 2 decades, the question should be settled. Either the void exists and explains cosmological anomalies, or it does not, and we need different explanations. Science will not remain uncertain indefinitely. The crucial point is that the question is answerable. This is not philosophy or speculation. It is empirical science subject to observational test. Nature will provide the answer. Researchers must simply perform the measurements and analyze the results honestly. Theoretical preferences and aesthetic considerations do not matter. Only data matters. The void hypothesis makes specific, testable predictions. It will stand or fall on whether those predictions prove accurate. Imagine the measurements come in. Cosmic chronometers show no difference between local and distant expansion. Baryon acoustic oscillations at larger distances reveal normal structure, indicating the underdensity does not extend farther. Gravitational wave measurements agree with local electromagnetic measurements, showing no distortion. Additional data fails to support the void hypothesis. The KBC void turns out to be less significant than thought, or our interpretation of it was wrong. What then? The Hubble tension remains. 2 robust measurement methods still disagree by 9% on the universe's expansion rate. This discrepancy demands explanation. If the void cannot explain it, something else must. Possibilities include unknown systematic errors in distance measurements, exotic properties of dark energy, unexpected neutrino physics, or modifications to gravity. Each option requires new physics or unrecognized measurement problems. Systematic errors seem increasingly unlikely given the care with which measurements have been scrutinized. Multiple independent teams using different methods reach similar conclusions. Instrumentation has been checked exhaustively. Statistical uncertainties are well understood. Unknown systematic errors would need to conspire precisely to create the observed discrepancy. Possible, but improbable. Dark energy varying over time is more plausible. If dark energy was weaker in the past and stronger now, cosmic expansion history would differ from simple models. Local measurements probe recent epochs when dark energy was strong. Cosmic microwave background measurements probe earlier epochs when it was weaker. This could create the observed tension. But why would dark energy change? What mechanism drives the variation? These questions lack satisfactory answers. Neutrino physics might hold clues. Neutrinos have small but non-zero mass. The exact mass affects how structure forms and how the universe expands. If neutrinos have different properties than assumed, predictions change. Some models, involving sterile neutrinos, hypothetical particles that do not interact except through gravity, have been proposed. These models can alter expansion history subtly enough to possibly resolve tensions, but evidence for sterile neutrinos remains weak. Modified gravity is the most radical option. Perhaps general relativity, Einstein's theory of gravity, breaks down at cosmic scales. Maybe gravity works differently over billions of light years than it does in the solar system. MOND is one such modification, but others exist. These theories change how structure forms and how expansion proceeds. They can potentially explain multiple cosmological puzzles simultaneously, but they often struggle to match all observations and introduce their own complications. If none of these explanations work, physics faces a genuine crisis. Our best theories of cosmology would be demonstrably inadequate. The universe would be telling us we are missing something fundamental. This has happened before in physics history. Anomalies in Mercury's orbit led to general relativity. Unexplained atomic spectra led to quantum mechanics. Major breakthroughs often emerge from observations that defy explanation. The Hubble tension could be announcing the next revolution. The void hypothesis is attractive because it explains the tension without requiring new physics. It uses general relativity and standard cosmology but accounts for our irregular environment. It is the simplest explanation in some sense. But simplicity is not always correct. Nature may be more exotic than we imagine. Another uncomfortable possibility is that the tension is not a single problem but multiple problems combining. Maybe dark energy is slightly different than assumed, and we live in a modest void, and there are small systematic errors, and neutrinos have unexpected properties. Several small effects, summing to 9% disagreement, would be harder to disentangle than one large effect. Resolution might require fixing multiple issues simultaneously. The worst scenario is that we are missing something completely outside current theoretical frameworks. Perhaps the universe's expansion history is not what we think. Perhaps time and space behave in ways general relativity does not capture. Perhaps the concepts of distance and expansion need redefinition at cosmic scales. Such fundamental revisions would invalidate decades of cosmological research. Everything would need reconsideration. If the void hypothesis fails, cosmology enters unknown territory. The safety net of familiar theories vanishes. But unknown territory is where discoveries happen. Whatever explains the Hubble tension, whether void or something else, will teach us profound lessons about the universe. Being wrong is not failure. Being wrong is the path to being less wrong. Time does not stop. The universe continues evolving. The KBC void is not a static structure. It grows, empties, and changes with each passing million years. Understanding its current state is important. Understanding its future is crucial for predicting what the cosmos will become. Dark energy drives accelerated expansion. This acceleration affects voids more than dense regions because voids lack the gravity needed to resist. As space expands, voids expand faster than average. Their volume increases. Their density decreases. Over billions of years, voids become progressively emptier and larger. The void containing us is undergoing this process now. In 1 billion years, the KBC void will be noticeably larger than today. Its radius might reach 1.2 billion light-years instead of 1 billion. The density inside will drop from 80% of average to perhaps 75%. Galaxy clusters near its edge will be pulled farther outward. The shell of matter surrounding the void will stretch and thin. Eventually, the shell may fragment as its components spread too far to remain bound. In 5 billion years, the changes become dramatic. The void could span 1.5 billion light-years. its interior might contain only half the normal matter density. Many galaxies, originally inside the void, will have drifted to its edges or beyond. The local group, if it still exists as a distinct structure, will likely have exited the void entirely. We will find ourselves in the dense shell region, surrounded by neighboring galaxy clusters instead of emptiness. But even as the local group escapes our current void, it may enter another. Voids are everywhere. Exiting one often means entering another. The cosmic web consists of a network of voids separated by thin filaments. Traveling along a filament eventually leads to the next void. Truly escaping void influence requires reaching a major intersection point in the cosmic web, a massive cluster like Shapley. Even then, voids surround all such clusters. The universe is becoming progressively more dominated by empty space. In 10 billion years, voids will constitute 90% of cosmic volume. Most galaxies will find themselves in or near voids. Dense regions will be rare, isolated pockets, surrounded by vast emptiness. The contrast between voids and filaments will reach its maximum. After that, further expansion simply makes everything more isolated without significantly changing the relative amounts of structure versus void. In 100 billion years, a completely different regime begins. Stars and galaxies will have aged. Many will have burned out. Star formation will slow or stop as available gas is exhausted. Galaxies will become dimmer, populated by old red stars and stellar remnants. The cosmic web will still exist structurally, but it will be faint. An observer in that era would see little light. The universe will be dark except for scattered glows from ancient galaxies. In 1 trillion years, galaxies become isolated islands. Accelerated expansion will have carried distant galaxies beyond the cosmic horizon. Light from them can no longer reach us because space between us and them expands faster than light travels. Each galaxy or galaxy group will be alone, unable to see anything beyond a shrinking observable region. The universe becomes infinitely large but locally looks small and empty. Eventually, even galaxies dissolve. Stars escape their host galaxies through gravitational interactions. Planets are ejected from solar systems. Black holes evaporate through radiation. Matter decays or falls into black holes. The organized structures we see today come apart over incomprehensible timescales. Voids do not just empty of galaxies, they empty of everything. Space becomes truly empty, filled only with faint radiation and occasional particles. This is the heat death scenario. Maximum entropy, no structure, no energy gradients to drive processes. The universe becomes cold, dark, and utterly inactive. Voids win their ultimate victory. They expand until they consume everything. The lumpy universe we observe is a temporary phase. Void domination is the permanent future. But these timescales are so vast they defy comprehension. 1 trillion years is roughly 70,000 times the current age of the universe. Worrying about heat death is like worrying about the fate of your body's individual atoms. It is technically relevant, but practically meaningless. The void's growth over the next few billion years matters far more for understanding our cosmic environment. The void's expansion is both inevitable and ongoing. We live during an era of transition as it transforms from a moderate underdensity into a vast emptiness. The Milky Way is not alone in inhabiting a void. Voids are common features of cosmic structure. Hundreds have been identified in galaxy surveys. Each contains its own collection of galaxies, experiencing similar isolation to ours. Observers in those galaxies would face similar challenges understanding their cosmological observations. We are not unique. We are part of a widespread phenomenon. The Bootes void, discovered in 1981, was the first large void identified. It spans 330 million light-years across and contains unusually few galaxies. Observers in a galaxy within Bootes would see a similar situation to ours, though on a smaller scale, they would measure local expansion rates biased by outflow from their void. They would wonder why their neighborhood appears emptier than predicted. The Eridanus supervoid exceeds even the KBC void in size. At 1.8 billion light-years across, it represents the largest known underdense region. If observers exist in galaxies within Eridanus, they experience even stronger effects than we do. Their Hubble tension would be larger. Their local structure would be sparser. Their isolation would be more extreme. Studying how Eridanus affects observations from outside, it provides clues about how our void affects our observations. The Sculptor void, the Microscopium void, and dozens of others populate the observable universe. Each has slightly different properties. Some are deep with very low density, others are shallow with modest underdensity, some are nearly spherical, others are elongated or irregular. This diversity reflects how different initial conditions and environments lead to different void evolution, but all share the basic property of being underdense regions surrounded by dense shells. Galaxies in different voids make different observations. A galaxy in a small, shallow void might not notice significant effects. Its Hubble constant measurements would be only slightly biased. Its local structure would appear reasonably typical. Conversely, a galaxy in a huge, deep void would notice major effects. All its cosmological conclusions would be strongly affected by location. There is a spectrum of void influence depending on void properties and observer position within the void. This raises an interesting question. What fraction of galaxies sit in voids significant enough to bias observations? Estimates vary, but perhaps 20 to 30% of all galaxies inhabit notable voids. If so, roughly 1/4 of intelligent civilizations could face similar cosmological puzzles to ours. They would measure Hubble tensions. They would observe unexpected local structure. They would debate whether their location is special. Void dwelling is not rare. Conversely, 70 to 80% of galaxies exist in normal or overdense regions. Observers in those galaxies would not measure Hubble tensions from void effects. Their local observations would match cosmic average predictions more closely. They would find cosmology more straightforward. From their perspective, the universe would seem simpler and easier to understand. They would not appreciate how lucky their location makes their scientific efforts. Imagine a civilization in a dense galaxy cluster. They see hundreds of neighboring galaxies. Their night sky is rich with visible structure. They measure local expansion and find it matches cosmic microwave background predictions perfectly. They never encounter void-related puzzles. Their cosmology advances smoothly from observation to theory without location-based complications. Compared to them, we face an additional challenge simply because of where we live. Yet, living in a void also provides opportunities. We get to observe void dynamics directly. We experience firsthand how underdense regions affect observations. We can measure effects that galaxies in normal regions only infer theoretically. Our location, while complicating some measurements, enables others. Science benefits from diverse perspectives and environments. Void observations complement cluster observations to give a fuller picture. Additionally, voids may be better for observing distant objects. Fewer nearby galaxies mean less light pollution and less confusion from foreground structures. Deep space observations could be clearer from void environments. Gamma-ray bursts, quasars, and other distant phenomena might be easier to study without dense nearby structures obscuring views. There are trade-offs to every environment. Across the universe, observers in thousands of galaxies are experiencing void effects. Some recognize them, others do not. Collectively, these observations are teaching cosmology that location matters. The universe is not homogeneous enough to ignore where measurements are made. This lesson applies universally. We are one of many void-dwelling civilizations grappling with the implications. Modern astronomy has repeatedly downgraded humanity's cosmic significance. Earth is not the center of the solar system. The solar system is not the center of the galaxy. The Milky Way is not the center of anything. We occupy no special location. This narrative has been drilled into scientific culture for centuries. It represents progress from geocentric arrogance to cosmic humility. But the void complicates this narrative. We do occupy a special location, not special in the sense of being central or privileged, but special in the sense of being unusual. Most galaxies do not sit in voids as large and deep as ours. Our environment is statistically anomalous. This is not because we are important or favored, it is simply where we happen to be. But it means our perspective on the universe differs from typical perspectives. We are not average observers. This realization carries implications for the anthropic principle, the idea that physical constants must be compatible with life because we are here to observe them. Some cosmologists argue that fine-tuning of constants requires explanation, possibly through multiverse theories where different regions have different constants. Others counter that no explanation is needed beyond observer selection. We necessarily find ourselves in a universe compatible with our existence. The void adds nuance to these debates. If our location in a void biases our cosmological measurements, we must be careful about drawing universal conclusions from those measurements. When we measure the Hubble constant and find tension, is it telling us something about the universe or something about our location? When we observe the cosmic web structure, are we seeing typical structure or structure as it appears from an underdense region? Separating universal properties from local properties becomes crucial. The void also affects the famous question, where is everybody? If intelligent life exists elsewhere, why have we not detected it? Many answers have been proposed. Perhaps life is rare. Perhaps intelligent civilizations destroy themselves. Perhaps they do not communicate across space. The void suggests another possibility. Perhaps we are isolated by our location. If nearby space contains fewer galaxies, it contains fewer potential civilizations. Our isolation is partly environmental. The distance to the nearest technological civilization depends on how common such civilizations are and how they distribute in space. If they concentrate in dense regions where matter is abundant, observers in voids will be farther from neighbors than observers in clusters. The void increases our probable distance to other civilizations. Not infinitely, but perhaps by factors of 2 or 3 compared to typical locations. This could make detection much harder. On the other hand, the void reduces background noise. Fewer nearby sources of radio emission or other signals means clearer channels for detecting distant signals. Voids are quieter environments electromagnetically. If a sufficiently powerful signal comes from beyond the void, we might detect it more easily than observers in noisy cluster environments. The void giveth and taketh away. Philosophically, the void challenges the mediocrity principle. This principle states that Earth and humanity are mediocre, typical examples of what exists elsewhere. Nothing about us should be special. But if we live in an unusual environment, at least our location is not mediocre. Does this matter? It depends on whether location correlates with other properties. If life only or preferentially arises in certain environments, then unusual locations imply unusual origins. Some researchers speculate that life might be more likely in underdense regions because cosmic radiation is weaker there, fewer nearby supernovae, fewer gamma-ray bursts, less high-energy bombardment. Perhaps voids provide safe havens where complex chemistry can proceed undisturbed for billions of years. This is speculative, but it highlights that unusual does not mean unfavorable. Our void environment might have been advantageous for life's emergence and evolution. Ultimately, the void forces us to think carefully about how location influences what we observe and conclude. We cannot blindly assume our measurements represent universal properties. We must account for environment. This is not a failure of the cosmological principle. It is recognition that the universe is complex and observers sample it from different perspectives. Understanding our perspective is part of understanding the universe. We are not the center of anything, but we are somewhere specific, and that somewhere is unusual. Look forward 100 billion years. The cosmic microwave background has faded to nearly undetectable levels, cooled by expansion to a fraction of a degree above absolute zero. Most stars have burned out or will soon. The Milky Way has merged with Andromeda and several other nearby galaxies to form a large elliptical galaxy. This combined galaxy sits in relative isolation, surrounded by emptiness stretching incomprehensible distances in all directions. The void that contained us has grown. It now spans several billion light-years, merging with neighboring voids. The entire region is one vast underdensity. The shell of galaxies that once surrounded it has dispersed. Dark energy has driven those galaxies beyond the cosmic horizon. They can no longer be seen from our position because space between us and them expands faster than light travels. The observable universe has shrunk to encompass only our local galaxy, and perhaps a few nearby dwarf galaxies that remained bound. Future astronomers in this era will face profound ignorance. They will see only their own galaxy. They will detect no cosmic microwave background because it has faded below detectability. They will observe no distant galaxies, no large-scale structure, no evidence of cosmic expansion. Everything beyond a few million light-years will be dark and empty. Based on their observations, they will conclude they live in a static universe containing a single galaxy surrounded by infinite void. This conclusion will be completely wrong but completely reasonable given their data. They will have no way to discover the truth unless they find records from earlier civilizations, or unless some relic radiation remains detectable. The universe will have hidden its true nature behind the veil of accelerated expansion and time. Knowledge will have become impossible to obtain. We live in a privileged era. The cosmic microwave background remains detectable. Distant galaxies are still visible. We can observe large-scale structure and measure cosmic expansion. In a few tens of billions of years, all this will be lost. Future observers will not even know what questions to ask. They will be confined to ignorance by their late position in cosmic history and by the void's isolation. This realization is sobering. It suggests that much of what we believe we know could be similarly limited by our temporal position or location. Perhaps there are phenomena we cannot detect because they have faded or because we are too isolated. Perhaps the universe contains structures and processes beyond our ability to observe from our vantage point. Perhaps our cosmological theories, built on what we can see, miss vast aspects of reality we cannot see. The void's expansion is inevitable. Dark energy shows no signs of weakening. Cosmic acceleration continues. Voids will grow until they dominate everything. The universe will become a collection of isolated islands, each unaware of the others, each believing they are alone in an infinite emptiness. This is the future written by current observations and theory, unless something changes, unless dark energy is not constant, unless new physics emerges at extreme scales, unless the universe's evolution holds surprises we have not yet imagined. Science has been wrong before. The future is not guaranteed. But based on current understanding, emptiness is the destination. Living in a void gives us a preview. We already experience isolation compared to galaxies in dense regions. We already see less structure in our immediate neighborhood. We are already beginning the journey toward the lonely future that awaits all galaxies. The void is not just where we are. It is what we and the universe are becoming. The cosmos begins with a big bang, a moment of infinite density and energy. It ends with a vast, cold emptiness. Structures isolated beyond possibility of communication. Entropy maximized. Activity ceased. From everything to nothing. From unity to isolation. The void is the final state. We happen to live in one that formed early, giving us a glimpse of what awaits. Look up at the night sky. The stars you see are temporary. The darkness between them is permanent. The void is the truth. The light is the exception. We exist in a brief moment when structure survives before expansion, and time erases it all. Recognizing this does not diminish existence's meaning. It clarifies existence's rarity and preciousness. We are here, now, able to observe and understand. That window is closing. Eventually, only void remains. The greatest cosmic structure is emptiness. We live inside it. We are learning from it. And ultimately, we will return to it.